Yeah, so no, I'll be around. What do you think? Actually, what I have. I'll just like online that location you guys. I'll be like, fire Solomon, you're. I didn't think that lawyer tree was early. Oh, that's what I'm concerned about. That's A and B, right?
Okay, so did you give me this example? Dude, people at my class are so fucking stupid. I didn't even know how to midterm. I showed up myself. This is H, for God's sake. Do you think math students will be smarter than us?
Okay, class. Before we get started today, I had a couple of announcements. First announcement is office hours tomorrow will not be held. I'll have a makeup session on Thursday, so Thursday's office hour will be longer in case you guys have any homework questions. The other announcement I wanted to make was about the project, which all graduate students have to do, and undergraduate students are welcome to try it out. Remember, if you do the project, you can get on the graduate student scale, so that's an option for you if maybe you didn't do so well in the midterm and you feel like you could do very well in the final. The project that we've posted online is kind of a preliminary version of the specifications. The project itself is complete, so you guys can get started. But if we might fine-tune some of the specs as we go along. But certainly you can get started and make some architecture decisions and get your simulations set up and running. The other announcement is that next week I'm going to be out of town again. On Tuesday, we're going to have a guest lecture. Actually, Al Molnar is going to give a lecture on low-power transceivers. And in fact, that is the topic of your project. So this may give you some ideas for your projects as well. And Al is also an expert on low-power design, so he's a good resource to have for your projects. Okay, any questions or comments? The projects will, oh yes, in the back.
The Cadence tool for project?
Yeah, preferably use Cadence. It'll make life a lot easier for you. You don't have to, but for instance, you can't simulate the noise figure of a down conversion stage without Cadence or without an equivalent tool. So either ADS, Cadence, Mentor RF, whatever tool, Eldo RF, whatever tool you have access to. Okay. Any other questions? And these are also individual projects. Guys are encouraged to work together if you have ideas that you want to try out and you have discussions, but you should turn in a final report that is your own contribution. Okay. The project is due more or less on finals week, plus or minus a few days. There's no strict deadline. Okay, if there are no other questions, we can continue where we left off last lecture. Okay, so last lecture we started looking at a schematic of a bipolar mixer, and it looks something like this. So we had a tank tuned to our IF frequency at the output of a BJT. We used resistive degeneration and emitter bypass. We use emitter degeneration to stabilize the DC operating point, and we use emitter bypass to get good gain at RF frequencies. And then we drive the base of this transistor through a transformer with 2 windings on it. So this is our DC input signal that we bring in. That comes in through this winding and provides base current. And then we have basically 2 windings. One is our LO port, and the other is our RF port. And as you'll recall, the way this circuit works, as we saw last lecture, is we have a large LO drive that will periodically modulate, hence the word modulate. It's a mixer, so it does modulation. It modulates basically the operating point of Q1, and the RF signal is small and experiences a linear time varying transfer function. Okay? So let's draw the AC equivalent circuit for this and see how the formulation that we derived last lecture is basically more or less exact. Well, AC equivalent circuit's very simple. The emitter is grounded, this point's grounded, and so we just have the transistor with 2 input signals. So our transistor is grounded. It drives a tank. This is tuned at IF. This point, of course, is grounded by that bypass capacitor. And this is our LO. And this is our RF. Okay? And really, you can see now this is equivalent to a transistor with 2 signals in series. This is the LO signal, this is the RF signal. And we basically analyze what the effect of a large LO signal is on the operating point of this transistor, so we can directly apply what we learned last lecture. Okay? Any questions about this equivalent circuit? Yes, Debo.
So just a little before that, when you hook up a capacitor at the emitter to get high gain, like a capacitor presents a real negative real part. So how do you take care so that it doesn't cause you instability?
That's a really good point. So Debo's point is that this capacitor here causes stability problems, especially at high frequencies where this path dominates over this path. It's something you have to take care of, as a simple answer. Basically, you have to make sure that the equivalent resistance seen here, so R equivalent, is larger than the negative resistance that you see. So the resistance you see here is basically the resistance of this winding plus the transformed resistances of the LO and RF port. So usually these are both 50 ohms. They look like they're in series. So you have 100 ohms with a 1-to-1 transformation ratio, about 100 ohms looking out here. So you have to make sure that the input resistance is less than that. Yes?
If you make the REQ really high, then looking at the output of the emitter, you see inductive effects, right? So that makes it more oscillating.
Can you repeat that? Maybe you want to use a mic because people listening on the tape won't get it.
When REQ is really high, looking at the emitter, you see inductive effects because it's proportional to RS minus 1 over GM times something. So it's more prone to oscillation than it.
Not necessarily. I mean, there is. Al, you want to handle it?
I think what it is that you want actually make the effect RF small.
Yeah, that's what I'm saying.
Not large. So it shunts the negative R.
You need to shunt that.
Yeah, you might be right about that.
So a large GS.
Yeah, you guys are right. So what you want is this resistance to ground to be small. Yeah, you're right. In general, though, I mean, this is one particular circuit. In general, you want to analyze stability very carefully. And the point is you can design this and make it stable. Okay. All right, well, let's apply the analysis that we did last lecture. Last lecture we found that if we consider the LO signal alone, if we do that, then the collector current is given by this periodic function, where we've explicitly have written a Fourier series and we found last lecture that these coefficients were just these modified Bessel functions, and we made the condition is basically assume bias current is constant. Okay, playing musical pens here. Well, in that case, we can also define a time-varying transconductance, which is just the instantaneous value of current divided by Vt, or if you like, divided by Kt over Q. And we could say that the large signal output is basically the GM times a small signal output current is the GMT times, let's say, the input signal. Okay, and if we just substitute for GMT from this equation, we have QIQ over KT, this series, times the input signal. Okay? Is that pretty clear to everybody? Yes, Kevin.
When do we know to use the coefficients for the Taylor series as opposed to the Bessel function? Expanding IC.
So last lecture we talked about the fact that this analysis is true, so this power series is true independent of B. B is the amplitude of the signal normalized to KT over Q. So I could put in 300 millivolts, I could put in 400 millivolts. Taylor series expansion is only valid for basically small signals, weakly nonlinear signals. And the way you would know if Taylor series expansion is valid or not is you would basically look to see how many terms you'd have to carry to make the Taylor series expansion valid. So remember that, for instance, for an exponential, you normalize everything to KT over Q. So if your signal is smaller than KT over Q, a few terms is very accurate. But if your signal is larger than KT over Q, you may find that actually you need 7 or 8 terms to make the terms basically all add up. Okay. Okay, so basically you can see now that the output signal is going to contain the RF input signal with multiplied by some gain, by some transconductance, times basically this term here, which is the product of two cosines. So let's call this omega naught the LO frequency, and this is the signal frequency, and this term here will give us a sum and difference frequency component. So I could say that the IF component of the output is the signal times this coefficient, basically. I could say plus or minus, but let's say I'm picking the IF. Well, okay. Depends on if your IF is lower or higher in frequency. Okay? Now this is the IF current. Then this flows into our tank, and the tank will filter out all the other frequency components that we don't want and select this frequency component. So this is the IF frequency. Okay. Now, interestingly enough, you could see that the gain basically is a function of B. And that means it's a function of the LO amplitude. So what we can do is we can plot this gain Let me see if there's a pen here. Oh, that one's bad. We can plot, let's say, a normalized gain. Let's call this the conversion gain, divided by GMQ. GMQ is the small signal GM of the device, and the curve will look something like this, where this is 1, and this axis is B, which is the LO amplitude normalized to KT over Q. And so this might be a B of 2, this might be a B of 4, B of 6, 8, and this is 0.2, 0.4, and so on. And so you can see now very clearly, this goes back to a question that was raised last lecture. How large does the LO amplitude need to be? And also related to your question today, Kevin, about the Taylor series analysis. The Taylor series analysis is kind of valid in this region. Okay, but in this region, you see that the conversion gain is actually quite low. So to maximize the conversion gain, we need to apply a very large LO signal. Okay, questions? GMQ is basically the GM for small signals. It's just basically IQ divided by VT. Right? So basically, I'm essentially plotting this coefficient here. This curve here is just I1B over I0B. All right. So another interesting question is, okay, I've designed this circuit now, and I make the LO drive large enough so that I get good conversion gain out of this. Question is, though, what's the input impedance looking from the LO port, and what's the input impedance looking in from the RF port? The reason I need to actually examine that carefully is because the signal at the LO port is quite large. So the current that flows in at the harmonic, basically at the fundamental LO frequency, is determined by large signal characteristics of this device. So it's not simply R pi, or beta over GM. We need to actually calculate what the input impedance is seen looking into the base of this transistor for large signals. For small signals, we could guess that it's just going to be R pi, and we'll show that. Okay? Is that clear? All right, so let's calculate the input impedance for the LO port. Well, the collector current we know is given by this expression. Okay, I won't repeat it. And so the input impedance at frequency omega naught is the input amplitude, we call this VO, the LO amplitude, divided by the base current at frequency omega naught, right? And the base current is just the collector current at frequency omega naught divided by beta. And if I substitute, I have beta V0, and this is the omega naught component, and that's 2I1B I0B times IQ, right? And I can write this, now I can write the LO amplitude as B times VT. So this is B times KT over Q divided by IQ 2I1B I0B. And you can recognize this expression here as being 1 over GM. Oh, this is a nice pen. Finally. So basically I have B over 2 beta over GM, I0b, I1b. So this is the input impedance seen at frequency omega 1, and I can just define a large signal GM. If I go back and look at the expression for GM, this is basically large signal GM times, excuse me, here. Here I can define this expression, this times this, as a large signal GM, and that pops up here as well. This is that term. So we see that the input impedance is actually a very nice intuitive result. It's beta divided by the large signal GM. Okay? So this is the input impedance seen at omega naught, and you can see in general it's going to be different from the small signal impedance. And so if you're impedance matching the LO port, you need to carefully calculate what input impedance is presented, which depends on the drive level of the LO port. Okay. Questions? Pretty clear? Okay, well, if you look at the RF signal, or the RF port, then the base current at the RF port is also the collector current divided by beta. And if we now look at the expression that we derived, we have basically a signal component, and then we have all the conversion components, the mixing products. And as far as the signal component goes, it looks like a linear circuit. So the input impedance is just Vs divided by component in IB at frequency omega s. And so that's just beta KT over QIQ, or basically just what we expected, the small signal input impedance. All right. Okay, so that means that if I basically look in from the LO port and from my RF port, I see different input impedances. Okay, let's generalize a little bit what we've learned so far. Yes.
So, like when you do, after all, this is one circuit, so the same current has to flow through the BJT. So, like when you do IC for to compute the impedance of the LO port, so you took only IQ1 plus 2I1B, and here you took another expression that's modulated by VI cosine omega t. But ultimately, the same IC has to flow. What's the difference?
Okay. So the idea is that the LO signal is very strong. So the dominant characteristics of the transistor are determined by the LO signal. And so from the LO port's perspective, you don't even see the effect of the RF port. It's so minor. It makes a very minor change in the input impedance. But from the RF port's perspective, the LO is very important. So that's why we separate it out. It's an approximation, but it's a pretty good one. Okay. All right, so let's make our analysis slightly more general. And in the case of a bipolar transistor, it's actually not too hard if we make the following approximation. Let's assume the collector current is the exponential function of the input voltage, as we have up to now. And the input voltage now is basically some LO signal, some input signal, and some bias signal. And so we can write that the collector current in general is some bias term times some LO modulation term times some signal modulation term. So this is the bias, this is LO modulation, this is signal modulation. Okay? And up to now what we did is we assumed that the signal modulation term was linear. But you can see that that's actually not really required. We can actually keep this exponential. Because this term is small, we can do a Taylor series expansion. Again, coming back to the earlier question. This term here, though, is not necessarily small, so we can't do a Taylor series expansion on it. But this term certainly is small because the input signal is small, and we can do a Taylor series expansion. So if I do that, I know that this LO modulation term gives me this Fourier series. And then the signal modulation term gives me this Taylor series expansion, where I've just written down the linear terms. So now we can see that the output signal consists of bias plus basically LO terms plus the conversion products, which not only include conversion of the fundamental of the signal, but also conversion of all the harmonics of the input signal. Okay? And so, for instance, if we had a two-tone, we could do a two-tone test to determine the nonlinearity. For a two-tone test, we assume that we have two signals, and basically this term now should contain those signals. So we have IC is IS e to the VA VT times e to the B cosine omega naught t times, now our Taylor series expansion will contain fundamentals plus basically square terms plus cube terms and so on and so forth. And we know from our previous analysis that these terms generate IM products. Okay? And these IM products actually can fall in band, for instance, right? So from a cubic term, we know that we'll get IM tones which are near these two frequencies. And because we multiply by this term here, we know that multiplication by the omega naught term will actually generate distortion products in band as well. Okay? Is that a question?
Could you write a little bit bigger?
I'll try. Okay. Okay. So the point is that so the IM products also get frequency translated to IF. And so we see that the mixer is actually also a nonlinear circuit. And the only thing that's funny is that if there's a frequency conversion going on. So I come in with two tones on the input, and then on the output I see my two tones, but then I see my intermod tones also down converted. So these are the IM products down converted. Okay? So I can now ask you guys, for instance, to calculate the IM3 of a mixer. And what we're talking about is the output signals are at the IF, the input signals are at RF. But all the same principles apply. It's just a shift of the frequencies to your IF, either up or down. Okay? Now the mixer circuit that we drew is actually pretty nice. The reason it's nice is because it allows us to sum two signals that are referenced to ground in order to drive the mixer. But it does require a transformer. And transformers are either bulky, or they're not available, or they're too expensive, or they may actually not operate at the frequencies of interest. So another version of this circuit, which kind of works a little bit differently, it's more amenable to integration, would have an RF input signal coming in as a current, driving a tank, and this actually could represent the LNA, so this could be your LNA as a transconductance device. And basically that again will drive our BJT stage, just as before, but instead of using a transformer, we're going to capacitively inject our LO signal. So here's the LO signal capacitively injected. And the way this circuit works is, so let's just say this is not convenient. Due to the transformer. The way this circuit works is, let's assume the LO frequency is bigger than the RF frequency. Okay? If that's the case, then this tank, basically above resonance, this tank essentially looks capacitive, so this capacitor dominates. So you can think of this LO signal as being capacitively divided and driving this signal. So the equivalent circuit looks something like this. So from the LO perspective, this is what the circuit looks like. Let's call this CS, LS, RS. This is our LO signal. And this is equivalent above resonance to basically a cap divider. And so again, we assume that this is a large signal, and so this modulates the operating point of our transistor, and then from the RF signal's perspective, we assume it's again a small signal circuit. And so the RF signal would basically flow onto parallel combination of this resistor and the input impedance, produce a voltage, and that voltage would get frequency translated due to the time varying transconductance. Okay, questions? Yes?
In your calculations, did you neglect the time variance of the device itself, like tau?
Yeah, we did. We assumed the device is very fast. So this circuit, if you wanted to take that into consideration, that would mean operating close to the FT of the device. So we're assuming that you're operating much below the FT.
Why did we have to include the transistor for the LO?
Can you come again?
Why did we have to include the BJT for the LO circuit?
This transistor here? Yeah, you don't have to. So this is just how you might implement it, for instance. Yeah, you could just have an LO signal to ground. Yeah, and as I've drawn it here.
So how is this different from the transformer circuit? I mean,
there are no transformers. That's what's different.
Yeah, but
got rid of the
could
transformer.
have just. I mean, I don't see any difference.
There's a
Besides,
big
like, we
difference,
didn't
right?
include the
There's no
transformers.
transformer.
Yeah, we didn't include
Yeah,
transformers.
obviously the circuit works the same.
Okay.
That was the purpose, was to use the same circuit, but to get rid of that transformer. Okay. Well, another thing that you may have noticed is that you don't have to necessarily mix off of the fundamental. You could also mix off of another harmonic. Let me go back to the equations here. So here, for instance, you can see that there's a term at twice the LO frequency, right? This second harmonic. And my input signal can actually mix with this and produce mixing products. And so I could select for this conversion product at the output by tuning my filter appropriately. And the advantage of that is that I can use a lower frequency LO. So for instance, I could have a second harmonic mixer where I drive it with an LO, but internally I use twice LO to do the mixing. So let's do an example. Let's say the LO is at 500 megahertz, the RF is at 900 megahertz, and I want an IF of 100 megahertz. Well, the way this works is that the IF is using twice the LO minus the RF, which is 1000 minus 900, or 100. Okay? And likewise, I could use 3 times the LO, or 4 times, or n times the LO. Well, of course, there's a penalty to be paid, and that's that the gain is lower. So the conversion product for the nth LO is the IF current divided by the input signal, and you can easily show that that's Gn over 2. And so for the bipolar, it's GMQ IN beta or B I0B. And as you make basically n larger and larger, this conversion gain gets smaller and smaller. So conversion gain is lower for large n. The advantage, though, is that I can use a lower frequency LO, means basically less power, and I can also get better frequency separation. So it's slightly more convenient. Okay. Now this this mixer that we've analyzed in a good amount of detail is actually really not used, right? If you go out there and look at real mixers, usually you don't build mixers this way. It's a very good mixer to study because all the equations all work out, and it's nice and analytic. But practically, it has some problems. One is it's a very nonlinear mixer. That's because the exponential characteristic is also very nonlinear. And generally, we'd like our mixer to be as linear as possible, especially because it's following some gain stages. So its linearity is that much more important. Well, if you go back and look at, data sheets from 20 years ago, 30 years ago, you will see that this mixer was used in cases where you needed a lot of conversion gain and you only had 1 or 2 transistors to play with. It's nice because it only requires 1 transistor. A lot of the other mixers that we study with bipolar will require 3, 6, 7 transistors. So if you're building this discretely, obviously it's really hard to do it. But in an integrated circuit environment, transistors come very cheaply. So this is kind of classic RF design. Let me just briefly also touch upon a FET mixer, so single transistor. And I'll probably just skip the details and let you guys look at the notes because it's very simple. The nice thing about using a FET device is that it's square law. And so ideally, it's extremely linear as a mixer. The square term gives us a product term, and then there's no more intermodulations occurring. So we know that as long as this device is in forward active, the current is just VGS minus VT squared 1 plus lambda VDS. Okay? And so this is the nice square law term. If it were really true, it would be a perfect mixer in some sense. Okay? And basically, if I apply a large signal, the drain current would have some DC bias term plus some bias point shift. This is due to the square term. I'm assuming here I'm not doing anything to try to keep the bias current constant. And then it would have an LO modulation term, which is basically the cross product term when I do the square here. And finally, it would have a second harmonic LO term. Okay, so let's call this the LO modulation, and this is the basically LO to LO harmonic. And so now I can define a time-varying transconductance, which is just basically due to this term. So let me do that. I have my drain current. So G of t is just a derivative of I with respect to VGS. And if I just plug in here, I get mu Cox W over L, VGS minus VT, 1 plus lambda VDS, where VGS is basically VA plus V0 cosine omega naught t. And so then I substitute this term here, and so I have VA minus VT plus V0 cosine omega naught t, 1 plus lambda VDS. Let me factor this term out. That will give me GMQ, the small signal GM, and then basically the time varying component, which is a function of the LO voltage normalized by the overdrive. Okay? So this is almost ideal. It's because my transconductance has a term which is just proportional to cosine omega t. If I could get rid of this term here, that would make it an ideal mixer. It would just have a GM that varied perfectly sinusoidally. Okay? So let's see how you build a mixer out of this. Well, you can use the same kind of circuits that we discussed already to generate a sum of the LO and signal frequencies plus some bias, and then you just filter the output at the desired IF frequency. And so the current I out is G of t times the signal, which is GMQ 1 plus V0 VA minus VT cosine omega naught t times Vs cosine omega st. And so that the IF component of the signal is GMQ divided by 2 V0 VA minus VT cosine omega naught plus or minus omega s t times Vs. Okay, I'll stop there to take any questions. Okay. So that means the conversion gain, which is the IF current divided by the input signal, is GMQ divided by 2 ratio of V0, the LO amplitude, normalized by the overdrive voltage. So this is an interesting result because GMQ is just a ratio of the current to the overdrive voltage as well. So if I say that GMQ is mu Cox W over L VA minus VT, then you can see that the conversion gain simplifies to just mu Cox over 2 W over L times V0. So this is my LO amplitude. And this is the transistor geometry. This is basically kind of fixed, independent of bias. So that means that GC is not a function of bias. So the assumption here is V0 is not large enough to basically cut off the transistor. So we assume that it's always in saturation. Okay. Now, this analysis is pretty valid for a long channel transistor. For short channel devices, there's some simplifications we made. Obviously, the current is not going to be square law, and we've also neglected the fact that the output impedance is not a constant. It varies as the drain voltage varies. And so for a real mixer design, you actually have to use the more complicated equations, but certainly these are some good starting points for the design. Incidentally, it's interesting that this single transistor mixer is still useful. one of my students designed a 60 gigahertz mixer based around a single transistor. So he used basically the nonlinearity of this device at 60 gigahertz to build a mixer. He used a single transistor because at really high frequencies, when you put multiple transistors together, as you know, the frequency response starts to suffer. So a single transistor is a good way to get a nice high frequency mixer device. Okay. Actually, the same student also explored what are called dual gate mixers. And in most modern technologies, you actually don't have a dual gate transistor, but you have the next best thing, which is a cascode device. So what I'm going to do is I'm going to apply my LO signal at the cascode gate, and I'm going to apply my RF signal at the transconductance gate. And the reason we call this a dual gate mixer is that you can lay it out with a shared junction. So this is gate 1, this is gate 2. Because I don't need to contact this point, I can make this junction very small, so that minimizes the capacitance at this node. And this is the source, and this is the drain of the second transistor. Okay. Now how does this mixer work? The way this mixer works is that from the small signal perspective, from the signal drive, this looks like basically a transconductance device, right? From the LO drive, it basically just sees a capacitance, which is the capacitance of M2. But if the LO drive is large enough, it will basically move this voltage up and down, right? From the LO perspective, this looks like a follower. This looks like a current source. So this voltage will practically replicate this voltage here. And you can see that when this voltage goes low, if it goes low enough, it might take this device into triode region. Okay? And what happens is in triode, the GM of the device gets much smaller. So if I actually bias the circuit very close to the point where this device is just in saturation, a large LO signal will modulate the GM of this transistor significantly because it'll push it into triode half the cycle. Okay? Does that make sense? So let me write that down. LO signal is large enough to move drain of M1 into triode region, right? If the drain drops below VGST of the first device. Now, what's the advantage of this circuit? Anybody? Yes, Debo?
LO and RF signals are isolated from each other.
Yeah, there is some degree of isolation between the LO and the RF. And also, I don't need to sum them. Remember, to sum the signals, I either had to use transformers, or at high frequencies, I use couplers, or some scheme had to be invented to try to get these signals summed together. Here, I don't have to worry about it. I just basically can separate them. And as we'll see later on in this course, the leakage of the LO signal into the RF path is very important, right? We call that the LO leakage. And so here, the LO is kind of isolated through these extra capacitors here. So there's minor amount of LO leakage, especially if this capacitance is small and the source impedance is small as well. Whereas in the single transistor mixer, there's quite a considerable amount of LO leakage because you're summing the signals. So unless you have transformers and you've designed them to provide isolation, you're going to get a considerable amount of leakage. Okay. Let me draw a couple pictures in case this mixer still doesn't make too much sense. Okay, so here is a curve, and this vertical line, let's say, separates the triode region from the saturation region of the device. And let's say that I bias my device so that this is the drain quiescent point. Then my LO signal basically will push me either further into saturation, where the GM remains constant, or into triode, where the GM drops. So the GM in saturation for a long channel device is mu C ox W over L VGS T. The GM in triode is mu C ox W over L VDS. So as the voltage goes lower and lower, the VDS drops and the GM drops accordingly. Okay. So if I had to plot my GM as a function of time, then it would have some nominal value, then it would drop, go back to the nominal value, drop, go back to the nominal value. So this is GM max, and this is basically the triode region. Okay. And in theory, if you made your LO signal really strong, you can really push this so that the GM goes practically down to 0. So this is a large LO. And it starts to look like your GM is basically a square wave with frequency of the LO amplitude. Okay? So you could see that GM of T approximates GM max times a square wave. So this is a square wave. Of unit amplitude. And anybody off the top of their head know the first harmonic of a square wave? It's 2 over pi actually. We'll see that in a second. So basically your conversion gain in the limit of a very large LO drive would go to GM 2 over pi. Okay, any questions or comments about this? Okay, so next lecture we'll start to look at different mixer architectures, which are called basically switching mixers or commutating mixers. Where the whole goal of the mixer will be to try to replicate some kind of switching function just like this S of t. Before we do that, though, I wanted to talk a little bit more about the theory of mixers, and in particular, noise of mixers. Now, we're not going to do a detailed analysis of noise of mixers, but I wanted to give you guys an intuitive understanding of why the noise of mixers is considerably higher than the noise of amplifiers. Okay. All right. So we're going to do some mixer analysis. Let's first start in the time domain. Okay. So in the time domain, what we see is that mixers that we've designed are essentially linear systems, if we assume the input signal is small enough. The only thing is that the gain is periodic. And the periodicity is basically T is 1 over omega naught, which is the LO frequency. Right? So this is a pretty generic model for all the mixers that we've looked at so far. The single BJT mixer, the single FET mixer, the so-called dual gate mixer. And next lecture we'll see that this model can also be applied to all the mixers that we study. Okay? Now, because h of d is a periodic function, I can write a Fourier series for it. Where Cn basically are the dot products of these complex exponentials with the function h of t. Okay. Now if we assume that the input signal is some fixed frequency signal, and I write this also as sum of complex exponentials, then the output signal is a sum Cn e to the j omega 1 plus omega n t plus e to the j omega naught n minus omega 1 t, all divided by 2. Okay? Questions? Yeah. So there's an AT term here as well. Thank you. And because this is a real function, h of t is a real function, I know that c to the minus k is equal to ck. These coefficients are even. And so you can see that I can actually start, for instance, if I take the c1 term, for instance, I have c1 e to the j omega 1 minus omega naught t plus e to the minus, let's say, plus omega n minus omega 1 t divided by 2 a of t. And then I have the c minus 1 terms, which is also going to be equal to c1, which is e to the j omega 1 minus omega n t plus e to the j minus omega naught plus omega 1 t divided by 2 a of t. And now you could see that I can group terms here. These two terms group together. These two terms group together. And so I have c1 cosine omega 1 plus omega naught t a of t plus c1 cosine omega 1 minus omega naught t times a of t. And there's other terms. Okay? And if you do the analysis a little more carefully, you'll find that the other terms basically all give us Cn cosine omega 1 plus n omega naught t, where n goes from all negative integers to all positive integers. Okay? So this is actually quite trivial. We've seen this happen with the bipolar mixer. The idea is that the output gets shifted by not only the LO frequency, plus and minus, but also by all its harmonics. Okay? We can see this in a slightly different way, equivalent way, in the frequency domain. It's always fun to look at a problem from different perspectives. If I multiply in frequency, then what do I do? If I multiply in time, what do I do in frequency? I do a convolution, that's right. So I take the convolution of h of f and x of f, and because h is a periodic function, we just prove that its frequency domain representation is basically a bunch of tones, right? A bunch of delta functions. So this is the representation of h of f in frequency. So this is f naught minus f naught, 2f naught minus 2f naught, and so on and so forth. And so now if I substitute into the convolution I have Cn delta of sigma minus nf naught, x of f minus sigma d sigma. And as you can see here, the right thing to do is to interchange the order of summation and integration. Because an integration with a delta function is very simple. You just pick out the value of the function where you've basically centered your delta function. So this integration is trivial. Since I integrate over all range, I know that I will in fact hit the center of my delta function, and so the output is as follows. So this is the input. So this is the input spectrum shifted by all harmonics of LO. And important to note is that this shift is both positive and negative, right? I have negative coefficients here and positive coefficients. So I take my input spectrum, shift it all to the right, and shift it all to the left, right? So let me do a picture here. Let me say, let's say that my input spectrum looks like this. So this is my input. And let's say this is my LO. This is my minus LO. And so the input spectrum has to be an even function. Okay? And so, for instance, if I take x of f plus f naught, that shifts this right. So this coefficient would be C1. So this would be, let's call this omega s. So this would be omega s minus omega o. And the same term here, if I do the same thing here, I get a shift to the left here. So this would also be due to C1. It would be this guy moving. Well, I also shift this right due to the minus 1 coefficient. So this would move to minus IF. This is plus IF due to C minus 1. And this would also shift right due to C minus 1. Okay? So this is my IF frequency down conversion. And now you can see that, now you can begin to appreciate the problem with noise, because let's look at what happens to noise. So this is an example. Let me draw x of f to be clear. This is at omega s. Yes? Question?
So in this diagram, is it possible for have C1, which is our wonder signal, to fall on top of a CK, to fall on top of C1? For example, if IF is 10,
Sure, right? That's what the image problem is, right?
the image of itself, I guess, right? In this case.
No, because the image is right here, right? So I have an image here, right? So let's review the image problem. I have my image here and here. So this is the image. And when I shift this down by an LO, my image moves here. And when I shift this one up by an LO, this moves here.
Is it possible for the negative signal to move 2
Sure.
or 3?
If I have a signal around twice LO, so let me draw that in. So you can see that the image problem is actually more complicated than we saw last lecture. So initially we discussed the image problem for just an ideal mixer. But a real mixer has an infinite number of image problems. So let's say this is my LO, this is my twice LO. Let's again take, this is the input frequency. And so then this is my image. Let me draw it in red. Okay. And this is my minus LO. This is my minus 2 LO. And this is my image. Okay. And again, this is a bad picture, so I'll just make this the IF here. This is the minus IF. So things are going to get crowded. So we can see now that this will down convert, this will up convert, this will down convert, this one will up convert, and this is our classic image problem. But now you can see that if I potentially have signals here, these will mix with 2 times LO and fall into the same band. So these can also basically fall into the same band as well. Yes, we have a couple questions. Back.
what if you don't have an image, but like how we saw in Drake conversion, that if the minus part of your signal can also fold over on the same thing. But now since you have multiple LO tunes, can that happen even for a high IF and not a direct conversion case? That you have two actual frequencies and no image, and those two fold over, but the other way around and interfere.
Sure. Yeah, that can happen too. Yeah.
We just guarantee that LO and IF are not modal poles of each other.
That's not sufficient, right? No. Because now, basically, think about, so this is the image problem. You can also see that this is a big noise problem, right? Because if you put a really sharp filter, right? So the way one way to solve the image problem is we put a huge filter right here, right? We put a very steep filter. Actually, this is the desired tone. So this is the image reject filter. But if this filter actually has an impedance Z0 in a wide bandwidth, then it has basically the same noise power as the source. So there's actually going to be noise at all these harmonic frequencies that get converted. So even if there's no image, noise in these bands will all down convert to the same IF. And so in general, we could say that noise from image band and let's say harmonic image bands will down convert to the same IF. Of course, the conversion gain gets smaller and smaller because C2 is smaller than C1 usually in a good mixer. C3 is even smaller, and so eventually, after let's say the fourth or fifth harmonic, the amount of noise contribution gets to be pretty negligible. But nevertheless, the output signal noise power is much larger than the input signal noise power. So even an ideal mixer that has no noise but just is a periodic transfer function like this has a noise figure which depends on the sum of the magnitude of Cn squared. Yes?
The filter is good. The noise at these other points should be low, right? I mean, most of your noise also would be in the same place because the noise also rolls out.
So the filter will filter out the incoming noise, but it'll generate its own noise, right? Because if the filter looks resistive at any frequency, it can generate noise.
But that's white.
Sure, and it's white, right? And so some of it will fall into these image bands. Yes?
So in real circuits, how do you suppress the high order on the 2 omega L, 3 omega L terms in here?
Well, this filter helps a lot, right? So this filter will suppress signals. That's why we really, the reason the image problem, we focus on this tone is because this guy is nearby, so he's harder to filter. But these other guys at twice, third, fourth could be very easy to filter. So even a very relaxed filter can take care of these.
How about mix itself? How do you make C2 out of mix itself go lower?
How do you
make the mixer itself, the C2 channel mixer?
Oh, I see what you mean. Well, that depends on the nonlinearity of the mixer, right? So the amount of C2 depends on how much second order harmonic is being generated by the nonlinearity. For instance, a FET mixer has C2, but it has no C3, an ideal square law FET mixer. So this depends largely on the transfer function of the mixer. Okay.
Question?
Yes.
Can't you get rid of the second harmonics of a mixer by using a diff pair? Just generate odd.
Sure. We looked at, basically we also looked at a diff pair mixer, and I think you guys may be doing a homework on diff pair mixers, right? So a diff pair mixer looks something like this. So let's actually look at a diff pair mixer. So for a diff pair mixer, you apply an LO signal here, and you guys are going to do a homework assignment and show that the collector current waveform approaches a square wave for this device, right? Now, I could also apply an RF signal here. So I could take a sum of LO and RF signals and use this time-varying transconductance to generate a mixer. Okay? But actually, there's a better way to do it because, again, if I want to sum the LO and RF, I run into the same problem of one, isolation, and two, having it to sum them together. Another way to build a mixer, very much like the dual gate mixer, is actually to inject your RF signal here. So let's look at how you would do that. So if I inject my RF signal here, let me take a simple mixer like this. Let me take this to be the output. Let's assume it's low frequency, so just a capacitor. This is just an RC filter. I could put an inductor here to get more rejection if I want. I drive my LO signal here. I assume I have a very strong LO drive, but I inject my RF signal here. So this device converts my RF voltage into a current. And if I swing this circuit with a large signal, then let's assume I can swing it with an infinitely large signal, right? So let's say the LO is positive. This is Q1, Q2. If LO is positive, then this device is completely reverse bias cut off, and this device is forward active. So looking up, I see a device that's off, and I see a device that's on. So during the positive LO cycle, all my signal current goes to supply, right? During the negative LO cycle, it's the inverse situation. Q2 is on, Q1 is off, and so all my IF signal goes to the output. Okay? So it looks like the output current is basically my RF current times that square wave waveform that we discussed earlier, where this goes to plus or minus 1. Okay? And so the action of this transistor, let's call this Q3, is really just to turn your RF voltage into a current. So we call this a current commutating mixer. Because it looks, the action of this mixer is to multiply the input current by either plus 1 or 0, ideally. Okay? Now, realistically, if you have a finite amount of LO drive, it's going to look something like this. Right? And because the role of Q1 is just to generate a current, I could easily also degenerate this device to make it more linear. In fact, I could use emitter degeneration to get a real input impedance in case I want to have a match. For instance, this might be driven by a filter, and the filter likes to be terminated properly, so I use emitter degeneration to terminate it, and then I go into what's called a current commutating mixer, or another common name for it is a Gilbert cell mixer. In fact, I can take the output differentially. So this is differential IF. Q1, Q2 basically are a Gilbert cell mixer, Q3. Basically, this provides impedance matching and linearity enhancement. Because, again, if you look at this circuit diagram here, or this equivalent equation, if it really were a square wave, from a current perspective, this is a perfectly linear mixer. It generates no nonlinearity. The only nonlinearity is basically in this IRF, right? And so if I make this very linear, this transconductance stage, I can make this very linear. So this is a differential version. Okay. Let me talk a little bit about balance. So let's talk about definitions. You'll hear the term unbalanced mixer, single balanced mixer, and double balanced mixer. And what do we mean by that? Well, mathematically, if the output signal is a product of 1 plus cosine omega naught t, this is my LO signal, and 1 plus cosine omega st, which is my RF signal, let me actually put some coefficients in here. Let me make this A0 and B0. If A0 is less than 1, then this is always positive, right? So this is, the polarity of this never changes. If B0 is also less than 1, then the polarity of this term also never changes. So these are unipolar signals being multiplied by each other, and this is basically an unbalanced mixer. And the way you can see that it's unbalanced is that because I have a constant term here, I get LO leakage to the output. This term times 1 gives me LO leakage. This term times 1 gives me RF leakage. So an unbalanced mixer has LO leakage, and it also has RF leakage. Okay? Now let's suppose that I could make the circuit balance with respect to one of the ports, like this. Or vice versa, I could have the other port balanced. This is a single balanced mixer. In this case, the LO port is balanced. And so what you see is that the LO signal does not leak to the output. Sorry, the RF signal is balanced. So LO port, LO does not leak to output. But the RF still leaks into the output. So let's see how our mixer behaves. Okay. Now if I take this version of the mixer, where I take the output single-endedly, if I analyze this circuit as equivalent multiplication by +1 and 0, then there is a DC component in this waveform. And so basically the LO signal will make it to the output. That's because there'll be a tone at the LO frequency at the output, and the RF frequency also leaks to the output because it gets multiplied by this DC signal. So this is a single balanced mixer. We have LO leakage. Sorry, this is unbalanced. Thank you. We have LO leakage and we have RF leakage. It's single balanced if we take a differential output. That's because in the differential version, my output signal is basically either the output current either goes in this direction or it goes in this direction. And so from the output perspective, I'm multiplying my signal by either +1 or -1. So when the signal goes in this direction, the polarity is positive. When the signal goes in this direction, the polarity becomes negative, right? And because the DC value is 0, then there is no RF leakage. Which is nice. The more tones we can get rid of in a mixer, the better it is, because all these tones we have to filter out and they become problematic. There's also issues with, so let me leave it at that. So this is nice. Much prefer to go differential because we get rid of this RF leakage, but it would be nice if we could also get rid of the LO leakage, right? Then we would have a double balanced mixer. So next lecture we'll look at that.